Okay, so if we look at 12.2, we just did 12.1, which was composition functions. 12.2 is going to be something different. We're going to be talking about functions that are inverses of one another. So before we do that, the first thing we want to talk about is when is a function one-to-one? Well, let's review quickly. When is a function a function? When is an equation a function? Remember, an equation is a function if it passes the vertical line test. That's one thing. And remember learning that if you're looking at a set of ordered pairs, it is a function if none of the x's repeat. If none of the x values or x coordinates repeat, then you're looking at a function. So now let's take that one step further. When is a function a one-to-one function? Well, a function is a one-to-one function when not only do the x's not repeat, but the y's also do not repeat. So all of the x's are different and all of the y's are different. That's when you have a one-to-one function. So let's go ahead and let's kind of play with this a little bit. So here's an example. This is a chart that just has a conversion from Fahrenheit to Celsius. So if it's negative 31 degrees Fahrenheit, it means that it's negative 35 degrees Celsius, and so on. If it's 32 degrees Fahrenheit, that's 0 Celsius, and so on. Okay? It is a one-to-one function because if I wrote them as ordered pairs, these would be the x's. Do any of those repeat? Nope. And do any of the y's repeat? Nope. That's why this is one-to-one. Each input, or x, corresponds to exactly one output, the y. I always think a better way of thinking about that is x's don't repeat and y's don't repeat. Let's look at this one. Is this function a one-to-one function? Well, none of the x's repeat, which certainly means that it's a function. How about the y's? That's going to tell me if it's one-to-one. None of the y's repeat either. So that means yes, this is a one-to-one function. The actual mathematical definition says for a one-to-one function, each x value corresponds to one and only one y value. Okay, so that's actually the definition of function. And though each y value corresponds to only one x value. That's what makes it one-to-one. No y values are repeated. So is this one-to-one? None of the x's repeat. Do any of the y's repeat? They do not. So yes, this is one-to-one. How about this second one? Is this one-to-one? Well, I immediately notice that there are two 9s there. The y's repeat. No, it is not. How about this one? Do any of the x's repeat? No, they're 4 separate words. But do the y's repeat? Yes, the y's repeat. So that is not a one-to-one function. How about this one? Do any of the y's repeat? Well, if you were to actually write down these points, you could do that. But here the y is -2. What's the y for this point? It's 1, or -1, right? Because this is -1, -1. And how about here? That's 1, -1. Right there, the y's repeat. So the y's repeat. So this is not one-to-one. Again, the x's and the y's can't repeat. Now, what if you're looking at a graph? So remember, if you have a function, it passes the vertical line test, which meant that you kept drawing vertical lines through it. And as long as each vertical line hit the graph only once, it was a function. If a graph is one-to-one, it means it passes not only the vertical line test, but it also passes the horizontal line test. So if we look at this function, it passes the vertical line test and it passes the horizontal line test. No horizontal line is going to hit it more than once. If it passes both tests, yes, it's one-to-one. So this guy, this parabola, is a function. We knew that. Is it a one-to-one function? No, because if I draw a vertical line right there, for example, and in fact, if I draw almost all vertical lines, it's going to hit it twice. So this is not a function, a one-to-one function. Is this a one-to-one function? Well, it passes the vertical line test. Does it pass the horizontal line test? No. Is this a one-to-one function? Well, for crying out loud, remember vertical line isn't even a function, so it can't be one-to-one. So that's a no. All lines except for a horizontal line and a vertical line will be one-to-one functions. Okay, so now that we know what one-to-one function means, let's go ahead and let's find the inverse of a function. So, first of all, for a one-to-one function, we can find its inverse function by literally, and this is all we do, switching the coordinates of the ordered pairs of the function. That is, we switch the inputs and the outputs, or you switch the x's and the y's. So, this is really the point 0, 1, because we know it's x and f of x. This is really the point 1, negative 3. This is 2, 5. This is 3, negative 4. So I'm just rewriting this function as ordered pairs. To find the inverse of this function, I literally flip the x's and the y's. 1, 0. Negative 3, 1. 5, 2. Negative 4, 3. And 10, 5. And this is the inverse. So you're flipping what we call the domain and the range, which just means you flip the x's and the y's. Now, so that's what you do if you're given a set of ordered pairs. What do you do if you're given an equation? Well, if you're given an equation, like you can see we have in this example right here, you have to follow some steps. So definition, the formal definition, so the inverse of a one-to-one function is the one-to-one function, and we use this notation, F inverse, that consists of the set of all ordered pairs y, comma, x, where xy belongs to the original function. So again, if these points belong to the original f, F inverse has these points. So here are the steps that you need to do if you're given an equation to find the inverse. So the first thing you do is you replace the f of x with a y. So if it's in function notation, which it will be, just pop a y in for f of x. The next thing you do is you interchange the x and the y. Here's what the definition says. What happens? The x and the y flip. Once you exchange the x and the y, you solve your equation for y, and then you put it in the correct form. So let's do those steps. The first thing I'm going to do is instead of an f of x, I'm going to write a y. Here's the key step now. I literally flip the x and the y. That one step flips all of the points. And now I take my resulting equation and I solve it for y. I need to get the y alone. So you can see that I would first subtract the 3, and then I just flip-flop sides of my equal sign. And we're going to divide by 2. So I found the inverse, but now I have to write it in the correct notation. So instead of the y, I'm going to replace it with f inverse of x. And this would be your answer. So again, just make the f of x into a y, because then you can flip the x and the y, take my equation and solve it for y, and then replace the y with the correct notation. Easy peasy. Now let's look at graphs of inverses. So if I want to graph the inverse function, it says the graph of a function and its inverse are related because the inverse is obtained by simply switching the x and the y. Thus, those two graphs of a function and its inverse will always be symmetric with the line y equals x. So let's first of all talk about what does that line y equals x look like. Well, that is the line where the x and the y's are the same numbers. So 0, 0, 1, 1, 2, 2, 3, 3, negative 1, negative 1, negative 2, negative 2, and so on and so on. This is the line y equals x. And when you have two functions that are inverses, they will always be symmetric with respect to that line. Let's show that here. So what I'm going to do is I'm just going to pick a couple of points here, and I'm going to flip the x and the y to graph the inverse. So for example, this point right here is 0, negative 4. I'm going to graph negative 4, 0. So that would be on its inverse. Let's see, this point right here looks like a good point. That's 6, negative 1. So I'm going to graph negative 1, 1, 2, 3, 4, 5, 6. And how about this point right here? That looks like a good one. That's negative 2, negative 5. So I'm going to graph negative 5, negative 2. So these are all points on the inverse. I'm going to do the best I can to graph that. So can you see that they are symmetric with respect to this green line? Any point up here has a matching point in the same position down there. And that will be true for any pair of inverse functions. Let's do the same thing over here. So I'm going to quickly graph this line y equals x. That is the line that bisects the first and the third quadrant. That's our symmetry line. So if I take some points from here, and if I draw the opposite, so like 0, 0, so that means that 0, 0's on my inverse. This point is 1, 1. That means 1, 1 is on my inverse. But how about if I take this point right here? This point looks like 6, 2. So I'm going to graph 1, 2, 1, 2, 3, 4, 5, 6. So my inverse function is going to kind of go like that. So do you see the symmetry with the matching points? So they'll always be symmetric with respect to the same line, and that line is always y equals x. Oh, great, there's a bug. All right, last thing we're going to do here. Determine whether the functions are inverses of one another. So what happens, okay, I have a bug right here that's going to drive me nuts. I'm in my basement. Okay, that bug is now smushed. That's gross, but it's done. All right, so what if I'm given two functions? How will I tell if they are inverses of one another? You have to use the definition. So if we look up it here, it says the original function takes the input x and maps it to the output y. The inverse function takes the y and maps it to x. So in general, we can say that if a function is 1-to-1, the inverse is the inverse such that, now look at this. Now this is our composition function. F inverse of f of x is equal to x, and f of f inverse is equal to x. So in English, what that means is, if I'm going to show that two functions are inverses of one another, I have to compose them both ways. I have to take my f of x and plug it into my inverse, and I should get x. And then I have to take my inverse and I have to plug it into my f, and I should again get x. If I get x in both cases, that means that those original functions were inverses of one another. So I'm going to find f inverse, or f of f inverse of x, and I'm going to find f inverse of f of x. I just wrote it in the other notation. And if I get x in both cases, it means that f and f inverses are inverses of one another. So here we go. This says that I'm going to take my inverse and plug it into my f. So that's going to be 2 times, now I'm going to plug this in for x. So again, all I did was I plugged this into here for x. Well, let's see. The 2's are going to cancel, and I'm left with x plus 5 minus 5, which is x. So I got x that time. Perfect. That's only halfway. I have to also go the other way. So the other way says that I'm going to take my f of x and I'm going to plug it into my inverse. So I'm going to take this and plug it into here. Well, let's see what that looks like. If I plug this in for x, it's going to be 2x minus 5 plus 5. And that's all going to be 2, which is 2x. These are going to cancel over 2, which is x. So I have shown, because I composed them both ways and got x both times, I have shown that they are inverses of one another.